So for the Lab 2C online lab, we're going to be taking this information, this kinetics information from the lab manual. It's the alternate lab of alternate lab 3. It's basically page 53 through 57. And the intent of this lab is to help you to learn how to analyze kinetics data. And that's sort of the clear goal, that we're going to have you sort of analyzing numbers, but also to connect these ideas with the theories of kinetics and why do we use kinetics and some of the classroom knowledge that you have about kinetics that's coming up. So things that we want you to get out of this lab is to understand that you cannot predict the order of a reaction. You can't, there's no way to figure it out except to do this experimentally. We figure out the order experimentally. We can then use that information to rationalize extra knowledge about the chemical reactions. Understand how to monitor a reaction. We typically, so there's a variety of ways, but we're going to talk about, I can sort of watch a reaction happening by monitoring the absorbance, which will monitor the change in concentration, and how to determine a rate order and the rate constant from using the method of initial rates, basically taking experimental data in two separate experiments and then using the initial concentrations and the initial rates to determine the order, and then using the order and those informations to find the rate constant. To compute a rate from concentration versus time measurements. So if I have a graph, if I have kinetics data, how do I actually find the rate? And then to be able to decide if a proposed mechanism is consistent with the experimental data, going back to the concepts. So I'm going to be basically focusing on the theory part, the questions, like 1 through 6, and then the last two, 19 and 20, in this concept portion of the lab. And then the more rigorous, the calculation stuff, will be in the second video. So if I were to sketch the concentrations of reactant A and product C versus time, what would they look like? We want to connect, what does this mean when we look at data? And so we kind of want to connect, what would I expect it to look like for 3A plus 2B makes C and 2D. So I know that reactant A is a reactant and it should go away, right? It's going to react, so I'm going to have decrease. I expect it to go down. I know that, so it should go down. Now, there's a variety of ways it can go down, right? It might go down that way. It might go down this way. It might kind of be steep and down that way. Maybe it will be like, it will still kind of go slowly, and kind of like this, maybe, real slow. So there's a variety of different things it can do. I know it's going to decrease. I also know that if it started at 0.7 molar, it should be 0.7 molar. And I know that it should end at 0, right? So this one I might have to drag out a long time to get to 0. But when the reaction is done, there should be none left. So I kind of know some stuff about it. All right, what about the concentration of product? Well, I know I start off with none, right? So it should be starting down here. And I know I'm going to make the product, so I should get more and more C as I go along, right? So maybe it's like this. Maybe, let's change colors again. Maybe it's like this. Maybe it's a lot at first and then it kind of levels off. Maybe, let's see, maybe it's a little bit at first and then more and more and more and more and more. That would be a little unusual, but so I know it's going to increase. Do I know where it will end up? I know it starts at 0. Do I know where it's going to end up? I kind of do, right? I know that if I start with 0.7 moles, let's assume I have 1 liter. So I start with 0.7 moles of A. And I know that I get 1 mole of C for every 3 moles of A. So 0.7 divided by 3, I don't know what that is, but whatever 0.7 divided by 3 molar is. It's going to be like 0.2 something. But we'll just leave it at that. So I kind of do know something about where it's going to end. So that's what we mean by sort of get a sense of what's going to happen. So I'm expecting when I get my concentration versus time data, it should kind of look like this. We're going to be monitoring a reactant, so we expect it to be more like the first one. Let's talk about different types of rates. We use a variety of different kinds of words to describe the rate. And in this case, this is a measurement. So consumption rate is how much of the reactant is consumed over time. So I know that consumption is going to be decreasing per unit time. It wouldn't really have a negative sign in here. It would be a value that would be negative sign. The negative sign is going to come when I sort of overall deal with it. It's going to be decreasing over time. So I need change in reaction over the change in time, but it's going to be decreasing because it's a reactant. Similarly, the production is going to be increasing. It's how much is produced. And so I know it's going to be increasing over time. So it would be, what is the increase divided by the change in time. Now, so how do I rectify the fact that one is decreasing and the other is increasing? And we already also saw that, yeah, but if I have different coefficients, how much it decreases and how much it increases is going to be affected by how many moles are needed for that particular reaction. So to sort of offset, I mean, I shouldn't have a reaction rate that is different depending on which thing I'm measuring, whether I'm measuring product reactant A or B, or whether I'm measuring product C or D. So how do I make sure that I get one universal reaction rate, irregardless of which thing I'm actually doing the measure, how I'm monitoring the chemical reaction? And so for this is where we sort of have an offset feature. Note that if I'm going to do a reactant, consumption rate, I'm going to put a negative sign in front of it, because a negative of a decreasing number would be positive. So this way I'm going to always make sure I'm getting a consistent number. If I have a coefficient of the product, the coefficient of the reactant, I'm going to sort of divide by that, and that way it will sort of offset for the fact that in our particular example with 3 A's making 1 C. So to sort of offset for that, I'll divide that rate by 3, because it should be 3 times faster since I need 3 of them. So same thing with if I use a production rate, I'm not going to use a negative sign, but I'm still going to divide by the coefficient of the product. So this way we get the same thing. This is just defining the rate as a measurement. How do we calculate the rate? This is not relating the rate to concentration or to the rate constant or to the order. That comes in the rate law. So when we're talking about just defining what the rate is or finding the rate, it's just about using measurement and going off of the change in concentration over the change in time. I can measure rates in a couple different ways. So how long of a period I measure it over will determine whether it's an instantaneous rate or an average rate. In an instantaneous rate, at a particular moment of time over a very short period, it's like sort of at that one individual moment of time, what is the rate going on there? Now, since the change in time, there isn't really a change in time, it turns out we would use take a slope of the tangent line at that point. So I would make a tangent to the point and I would take the slope of that line. That's how we would find it. You probably do that in class. The average rate then means over the entire reaction. So that's going to be, how much concentration did I start with? How much do I end up with over the total time? So it's sort of like the initial point and the final point of the plot. I would take a slope of those lines. I can sort of show you that on a graph. So we see this graph here. So this green one is the slope of the line from the very initial point to the very final point. So that would be the average rate. Whereas this blue line is really just focusing on the circled point. So I could draw a line tangent to the curve, and then I could take a slope of the blue line and get that value. That would be an instantaneous rate at time 50. So again, we would ratio it to what time it's at, because now it changes over time. In this case, I can see that if I were to draw tangent lines, I would have different slopes of those tangent lines. So this one is definitely showing that the rate is changing as time goes by. Now we get into the rate laws. We're connecting these ideas of measuring the rate back to the theory of kinetics and the theory of reactions. And the rate of reaction is going to be related to the concentration of the reactants. Generically speaking, if I had a 2-reactant reaction, rate is always equal to some rate constant times a concentration of a reactant to raised to its order, whatever the order of that is, times the concentration of the next reactant raised to its order. So we're going to call K this rate constant. And we're going to determine M and N experimentally. M is the order of the reaction with respect to reactant 1. N is the order of the reaction with respect to reactant 2. And the overall order would be M plus N. So now it's sometimes possible that the order is 0. And as you know, anything to the 0 power is 1. So maybe there's 2 reactants, but you don't see reactant 2 in the equation. That's suggesting that it's 0th order. And again, we would have to determine that experimentally. We'd have to say, no matter how much you change the initial concentration of reactant 2, it doesn't change the rate of the reaction. Okay, so if I were going to make an empirical rate law for this sample reaction, again, I'm focusing on the reactants. So it always is rate is equal to a rate constant, K, times, I'm just going to put that I have 2 different concentrations. I have reactant A and reactant B, and then this would be some order M and this would be some order N. It doesn't particularly matter which, we start with M and then we continue on alphabetically for other orders. Rarely do we have more than 2 or 3 reactants in an equation, so we only usually have 1 or 2 reactants. So this would be my empirical rate law. Now, what variables do I have in here? Now, so again, variables would be things that change. In this case, since time is the independent variable, we would be saying things that change with time. If I were doing something in kinetics, that's what we're doing. We're changing the time and saying which things are varying with time. So would the rate change with time? Yeah, I saw that on the prior curve. What about the concentration of A? A is a reactant. It should be decreasing. We talked about that. Concentration of B is another reactant. It should also be changing. Possibly not at the same way, but that doesn't matter. They're changing over time. And then that rate is a change in concentration over change in time, so that will be a variable. In some cases, it doesn't change with time if it's 0th order, but again, it's still something that could change with time, so we would call that a variable. Now, the parameters are things that aren't going to change with time. They are things that might change with a different reaction or a different temperature, but once I know them for a specific reaction or temperature, they're not going to change. So parameters would be something like the rate constant and the orders, M, N, and the overall order M plus N. So those would be things, once I find them, they're going to stay the same. We really can't call them constants, because a constant would be something that's always universally true and never changes, and it does change. This is something that changes for different chemical reactions or different temperatures, so I can't say it's a constant, but it's not a variable. It's not changing with time. So our job is to then use some stuff to find those. We're going to use this crystal violet reaction and try to find the M and the N. So we want to think about what things are we measuring, what things do we calculate for measurements. So directly things that we measure would be the rate, right? No, the rate is the change in concentration of the change in time. So we're going to actually have to calculate. We need at least 2 time periods to calculate the rate. What about the concentration of crystal violet, the reactant? Nope, it turns out there are ways to experimentally directly measure concentration, like with a titration reaction, but we're going to use that Beer's law that you did in 123, the idea that the absorbance, if it's a colored solution, and crystal violet is a brightly colored solution, that as this decays, the color is going to, the concentration is going to decrease, and when the concentration decreases, the absorbance will decrease. So we're going to actually measure the absorbance of the crystal violet and relate that to concentration. So we'll calculate that. And we're also going to measure the time. So we're going to measure time and the absorbance of crystal violet. But we can get a standardized plot. Remember when you did that, you took all the standards. I know some known concentrations of crystal violet, and I make a graph. I make an absorbance measurements for each of them, and I create a graph. I find the relationship, and from that I have a calibration plot that I can use to to relate absorbance to concentration. So I would have to do that before I did the kinetics experiment. And then I could take all my absorbance measurements and convert them into concentration. So it would be a calculation. I'm going to calculate the rate. We're going to do that specifically in this lab. We have a bunch of, we're going to give you them in concentrations, although technically they weren't measured, they were calculated. And then, and a bunch of times, and you're going to get the rate from that. We'll talk about how to do that. And then once I have two different experiments, I can get a rate constant. Again, that's going to be a calculation. And I can get an order of the reaction. That's going to be a calculation. So most of what we're getting here that we're interested in, even the things that we're going to analyze to get the rate constant in the order, are calculations. And this happens a lot. So there's a lot of calculations. It's a little easy to get lost. So let's talk about the method of initial rates, just sort of the general idea of it. We know that from the rate is equal to the rate constant times the concentration raised to the order. And I need to sort of simplify that down so I can just find the order. And the way I need to do that is I need to say, well, since those are parameters and they aren't changing, if I do it twice under two initial concentrations, starting concentrations, and take the ratio, I should be able to find the order of the reaction. So we measure the initial concentration of a reactant, we start the reaction, measure the concentration reactant over time, and from that I can get a rate for that reaction. I want the initial concentration and the initial instantaneous rate of the reaction. Then I'm going to repeat it with a different initial concentration. Generally in textbooks we always double the concentration so that this ratio here is a nice whole number of 2. But that doesn't have to be true. We can do any other different concentration, and then we're going to again do the same thing. We're going to get the initial concentration, start the reaction, monitor it over time, get the rate. So then I have 2 rates and 2 initial concentrations. Then I solve the ratio of rates for m. So again, if this is 2, then I have this ratio it's going to be 2 to some m. So either this rate ratio would be 1 if this is 0, or it's going to be 2, or it's going to be 4, or it's going to be 2 to the 3 would be 8, right? You know, so I can kind of determine the order of the reaction by looking for that pattern. And then and if I need to go on and find the rate constant, now that I know the rate order, I can plug it back into the equation with a rate and an initial concentration and solve for K. All right. Towards the end, after we do all that, and we'll do that in a separate video, we're going to come back to what do you do with this information. We might be able to write down an overall reaction for an equation, but I need to relate that to the overall reaction and the elementary reaction and figure out how this relates back to orders of kinetics. So if this is a reaction, but it occurs in 2 separate steps, it turns out that one step is generally slower than the other, and it's sort of the rate determining step, because you can't complete the second reaction until the first reaction finishes if the first is slow. If the second is slow, everything kind of backs up while you're waiting on that last step. And you know, we've seen this in a variety of activities that involve a variety of people doing a task. The slow person's, the task that's the slowest is the one that slows everything down and controls the overall rate of the process. So only one of the steps would be considered the elementary rate determining step. So these are elementary steps. These are the actual reactions that are occurring step by step, and the rate determining step would be the slow one. So if I know from experimental evidence, from advanced chemical knowledge, that one of the steps is the slow rate determining step, then the order of the reaction is the coefficient for that reactant. So in this case, if NO2 plus F2 making NO2F plus F was the elementary rate determining step, then I know that my rate law would be rate is K times NO2 to the 1 power, because there's a 1 coefficient here and a 1 coefficient. So this reaction would be first order NO2 and first order in fluorine. And again, so now if I can measure those orders experimentally and determine the order of the reaction with respect to different reactants experimentally, I can compare them to theories of different mechanisms, different types of steps, and see which ones are consistent. I mean, it doesn't prove that that's what's happening, but sometimes I can eliminate options and then at least get it down to a few possibilities. Okay, so let me sort of show you a specific example. This is a different reaction. NO, two NOs plus oxygen makes NO2. So in the first reaction, so I just have this proposed mechanism that two of these molecules of NO come together and make an intermediate complex. And then that intermediate complex meets up with an oxygen molecule and splits the oxygen molecule apart, and kind of the whole thing splits in half. So one oxygen goes with one and one goes with the other, and the whole thing splits apart, and now I make two NO2s. So the steps are the same, but in the first proposed mechanism, the slow step is the first one. In the second one, the slow step is the second one. So in this particular case, the rate I would expect if the first one was the slow step would be a rate constant with a second order of a reaction with respect to NO and zero order with respect to oxygen. So there is no oxygen in the first step. So since this is two NOs, I would expect it to be second order with respect to NO. If I had the second mechanism, the second step was the slow step, it would be rate is K2 times N2O2 times the concentration of O2. It would be first order in oxygen. Now, since this is an intermediate, it's not a reactant. So we would say this is first order in oxygen, and I wrote down here first order with respect to both NO. Would not be first order with respect to NO, just first order with respect to oxygen. Zeroth order with respect to NO. So I will get different answers. So now I can compare that to my experimental data to either include or exclude a possible mechanism, and that's where the power of kinetics often lies.